Okay. Okay. Yeah, it's better. Okay, let's come to the last speaker of today's session, Han-Chen Lee, and he's talking about randomized Bayesian inference and stochastic representation of model error. Okay, welcome, Han, and floor is yours.
All right. Okay, thank you. I hope you can hear me.
1 second. Switch.
Let me know if I hope I'm audible now.
Okay, this should be better.
Hello, can you hear me now?
Yes, I think we.
Can you hear me now?
Ah, yes.
Yes.
That's
okay.
better.
All right. Sorry about that. Okay, so I'll share my slides and I'll start my timer now because I've got 20 minutes. First of all, I'd like to thank the organizers for inviting me to give this talk and for organizing the workshop in the first place. And I'd like to thank the staff of the Newton Institute for facilitating online participation, and also for all of you there. I'm sorry I can't make it in person, but it's been very interesting to hear about what's being done in this area. So yeah, I can't see the chat. So if there's a question, if something's unclear, please just ask, okay? All right, so without further ado, let me get straight into the matter here. I'll be mainly considering mathematical questions, and I'll start from the point of view of inverse problems, whereby we have an observation model which tells us that our data y is related to some unknown true data generating parameter x star through a parameter to observable map or forward model G. And we're going to factor into the account that there's going to be some observational noise in our data. In the inverse problem is simply given the data y, infer the truth x star or the data generating parameter x star. For the Bayesian approach to this, since we don't know x star, we will model it using a random variable x with some prior law mu pri. We also choose a likelihood f of x and y such that, for example, if our observational noise we assume to be Gaussian with mean 0 and some covariance c, which is positive definite, then we can explicitly write down the likelihood in terms of a Gaussian density, where the norm or the data misfit is basically a norm weighted by the precision of the noise, so C inverse here. Given the prior mu pri and the likelihood f, we can then solve an inverse problem with the posterior mu y pos, which is obtained by Bayes' formula. The posterior is simply proportional to the likelihood integrated against the prior. Okay, so this slide is mainly to go over things which many of you probably know already, just to fix some notation. Okay, and as mentioned in the abstract, one of the guiding examples that I will, well, pretty much the only guiding example I will consider in this talk is the issue of time integration of a dynamical system. Suppose we have an initial value problem, or an IVP, on some finite time interval 0 to t, and we'll denote its unique solution by z for some fixed parameter x. So dz dt as a function of time is given by a vector field f here, and here this is not the likelihood, by the way, sorry for the abuse of notation. The vector field takes in the state of the solution or the dynamical system at time t, and we also allow for the fact that the vector field itself may depend on the parameter x. We also allow for the initial condition itself to be a function of the parameter x. So that's exactly what's written here. Given this initial value problem, we can define an associated solution operator S, which maps parameters to basically continuous trajectories. We can fix some time points t1 to tj in our time interval 0 to t, and use these to define an observation operator O, which takes a continuous trajectory z and basically maps it to the evaluations of the state at the corresponding times. We can then define a parameter to observable map G, basically as the composition of the solution operator with the observation operator. Now, one fundamental problem in many applications, including data simulation and geophysical fluid dynamics, is that the true solution map S, which basically tells us how to solve our initial value problem, it's not available. Perhaps our mathematical model is simply an idealized representation of nature, or we can't even work with that computationally. So the key constraint here is that the true forward model G is not available. This is just to remember what we saw on the previous slide. And the problem is that we can't evaluate the map that sends a parameter to the solution map exactly, because we don't have a nice closed form solution for this initial value problem. The solution then, as is usually the case, is we have to approximate the solution map. So we'll work with Sn, which is an approximate solution map that does the same thing effectively. It sends a parameter to a trajectory, and think of n here as an approximation level. So in the case of time integration, n could be, say, the length of the time interval t divided by your time step little h. Using this approximate solution map, we can then define resulting approximate objects, like the approximate forward model Gn, simply by composition with the observation operator. We can then pass this approximate forward model Gn to construct an approximate likelihood Fn in the usual way. And given the same prior and this approximate likelihood, we can then define an approximate posterior mu I n pos using Bayes' formula. So there are two questions here that we can ask immediately. How do we account for error in the forward model Gn? And second, how does the error in our approximate forward model Gn propagate to the error in the resulting or associated approximate posterior? So let's consider the first question. How do we account for error in our approximate forward model Gn? The answer is, well, if we don't know something, but we want to take into account somehow, one way to do this is to use random variables. So recalling our parameterized initial value problem as the example, suppose we use a deterministic time integrator, which I'll denote by psi, and you can think of this as implicit Euler, explicit Euler, whatever your favorite time integration method is. And it maps basically, it takes a state and it maps it to another state. And we're going to use a time step h. So basically this works in the usual way. We update at discrete times k from kh to k plus 1h. We just apply the deterministic time integration map psi. And having a collection of these states at the discrete times kh, we can then define an approximate solution map Sn by interpolating between these discrete states. The randomized time integrator with random variables, which we'll denote by psi k, and we don't assume them to be IID, is defined in an analogous way. Suppose we have a state, a random state z hat n at time kh, depending on a parameter x. We push it through our time integration method psi and add a random perturbation, a random variable psi k. And that gives us the state at the next discrete time k plus 1h. So the crucial thing here is that each time k, so psi k of h and omega, this models the error in the time evolution map psi over the time interval starting at kh and ending at k plus 1 times h. We can then do the same thing as we did before and define a random solution operator s hat n by simply interpolating between these states at the discrete times. And heuristically, s hat n tries to account for the error in our approximate solution map Sn using these random variables psi 0 to psi n minus 1. So as an example, here's a Fitsunagumo initial value problem. The precise ODE doesn't matter so much, but what matters here is that our right-hand side, so the vector field, depends on some vector of parameters theta, theta 1, theta 2, theta 3, appearing in the right-hand side as follows. And the solution map does what you expected. It maps the parameter to basically the solution of this initial value problem for some initial condition that I've omitted. Suppose we use as an approximate solution operator, basically interpolation with the implicit Euler map psi and some time step h. The randomized integrator does what we saw from the previous slide. We use implicit Euler and randomize at each step that we applied implicit Euler. And using interpolation, we get a random approximate solution operator s hat n of this Fitsunagumo initial value problem. What this results in is basically an ensemble of solutions to the initial value problem. In the top plot here, basically you see an ensemble of the discrete states or the trajectories with the discrete times. So each dot here is a discrete state. The black line is a deterministic solution, which we assume to be our truth at some really fine, at a much finer time step. And the blue dots are the means. So remember, we're plotting two curves here because the solution to the Fitsunagumo initial value problem is a trajectory in R2. And in the bottom, we've basically done some interpolation and we've smeared out these dots to plot confidence intervals. What does this actually do to the corresponding posteriors? On the left column, basically, you see the posterior that corresponds to when we don't randomize. And what you notice is that the posteriors, if you could call them that, are really concentrated. Where the dashed lines intersect, those are the true values of theta that we use to generate our data. And we can see that the posteriors, when we don't do randomization, are really concentrated. And as you would expect, when we do include randomization, the corresponding posteriors are much more spread out. So some kind of variance inflation is resulting from the fact that we randomize our time integrator. What's nice about this is that even at really coarse time steps, our corresponding posteriors are sufficiently spread such that we do have coverage of the true parameter values. Okay, so that's the key thing to take away from this slide. So now let's consider the true posterior associated to the true forward model G. I'm denoting it here. This is just a recap of what we saw earlier. What about the random approximate posterior mu hat y associated to the random approximate forward model G hat n? We can do basically the same thing, applying Bayes' formula and using the same noise covariance, so on and so forth. So what's interesting here is that each realization of our random approximate forward model G hat n yields a realization of a random approximate posterior. So we actually have an ensemble of posterior measures on our parameter space calligraphic X. So what can we do with this ensemble? We can just use one, we can just pick one member of this ensemble and pretend that we do inference with that, or we can do some averaging over the ensemble methods, over the ensemble members of this collection of posteriors. And I won't go into details about these two approaches, but I'll try and investigate this question of how does the error in the random approximate forward model propagate to the error in the resulting random approximate posterior. So this is just a recap of what we saw from the previous slide. And the answer to this question is given as follows: under some conditions on the true forward model G and the random approximate forward models G hat n, we have some Hölder conjugate exponents S1 and S2 and some scalar D that depends on this and this collection, but it doesn't depend on any n in per se, such that we can control in mean square the Hellinger distance between the true posterior and the random approximate posterior in mean square up to some scalar D of basically this nested integral. We first integrate the norm of the difference between G and G hat n with respect to nu n, which is the law of G hat n. So basically we integrate out the randomness in the G hat n, but these are still functions of X. So finally, we then take an expectation with respect to the prior measure, which is a measure on X. What's interesting about this is that it basically gives us some kind of local Lipschitz stability of the posterior, or more precisely of the random approximate posterior, with respect to perturbations in the true forward model. And this follows a long line of work starting with Andrew Stewart's Acta Numerica paper in 2010, and has been extended recently by Björn Sprunk in 2020. One can prove a similar local Lipschitz stability bound where we replace the Hellinger distance with the Kullback-Leibler divergence DKL. So here's this stability inequality that we saw earlier. It basically tells us if we can shrink this error, if our approximation is good enough with respect to the truth, then we can be confident that in mean square error, the distance of our random approximate posterior will be quite small with respect to the true posterior. So then the question is, how would we actually compute this right-hand side, in particular, the first expectation here? I'm just writing it out for simplicity or to make things a bit clearer. Well, let's go back to our time integration example here. And this is remember, our true forward model is a composition of an observation and a true solution operator S. And our random approximate forward model is done in exactly the same way, except that we replace S with S hat n. And we obtain S hat n by randomizing some deterministic integration using a collection of random variables and interpolation. So let's suppose for convenience that our observation operator O is given by observation of the trajectory at j times chosen from our discrete time grid. Then we can actually control the difference in the outputs of your true forward model with your random approximate forward model, bounded above by the number of time observations you take, times the worst case difference in the discrete states, or the states at the discrete times. So let's recall, this is our initial value problem, and I'm going to omit the dependence on the parameter for now, just for simplicity. Associated to this initial value problem is a true flow map phi, which basically just pushes forward. If I know the state of the solution at time t, and I propagate forward at time s, that's basically the output of this flow map phi. Using this flow map phi, I can construct a true solution sequence at the discrete times. Z of k plus 1 times h is just simply the output of phi if I give it the starting state Z of kh and propagate it forward in time by little h. Now let's choose a time integration method, psi, which hopefully is a good approximation to this flow map phi. Okay. We do what we've done before. We randomize the solution sequence basically by applying this deterministic time integration method and randomizing each time we do so. Now let's put some assumptions to make things a little bit more concrete. We suppose, first of all, that there exists an L psi, which is positive, such that for all suitable S, Z of t and Z tilde of t, basically we can control the difference in the outputs corresponding to this deterministic time integration up to a factor of 1 plus L psi of S of the inputs. So basically this just means that our time integration map psi is locally Lipschitz. Second, we assume that there exists a function C of phi and psi, and sorry, this should be a capital psi, that's bounded on bounded subsets. It's a function of time and the space. And we assume that there exists a Q, non-negative, such that basically we can control the local truncation error up to this factor C of psi and psi times the time S by which we propagate forward in time. So this just means that our deterministic time integration method psi has local truncation error of order Q. Third, we assume that there exists an Orlich norm. So if you're not familiar with this, just think of this as an LP norm in the sense of random variables. And we have a scalar P, non-negative, such that for all K and S, we can basically control this LP norm of each random variable that depends on the time up to some constant. It decays like S to the P plus 1. Okay, so that's basically the interpretation of this condition is that the Orlich norm absolute moments of these random variables decay like S to the P plus 1. And if you want, you can just replace S with a time step H, because that's what we're going to do later. That's typically what we're going to use because we're looking at psi k as a function of H. All right, so these are the assumptions that we put on not only our initial value problem, but also on our time integration method psi and our randomization as well. So here are the assumptions just to keep things from the previous slide. We now have a theorem. Under these assumptions, we can basically control the maximum error or the maximum difference between the true solution at the discrete times and the random approximate solution. This is a random variable. So we're going to take the Orlich norm or an LP norm if you want, with respect to the law nu n of the random variables psi k. Given these assumptions, we can control this worst case error as a function of the time step h to the smaller of q and p. So remember that q is the order of our deterministic time integration, and p is basically the parameter that describes how these LP norms of the randomization decay as s goes to 0. The key thing here is that z hat n, basically the discrete trajectory or the discrete solution of the initial value problem, it inherits in some sense the integrability of the randomization that we use to construct it. Furthermore, we don't actually require the psi k's to be IID or Gaussian. What have we done? We now can use this bound above and plug it into this bound that we saw from a previous slide, and in turn use that to control the right-hand side, of our local Lipschitz inequality bound, and ultimately to control the difference in mean square with respect to the Hellinger norm of our random approximate posterior with respect to the truth, which we don't have access to. Okay, and this brings me to the summary. We started with an inverse problem, which is quite ubiquitous in data simulation problems. We have some data, which is generated by some parameter to observable map from some unknown true data generating parameter x star, and we want to solve for x star. The complication is that in practice, we don't actually have G, we only have an approximation Gn of it. And we know that the error in this approximate forward model will propagate to some error in the resulting approximate posterior, mu y n plus. We want to account for this error somehow because that's something that is quite important, not only in data simulation, but in inverse problems more generally. And we do that using random variables. And that kind of fits because we're using a Bayesian approach. So it's all right to use random variables to model things that we don't know exactly. Doing this results in basically a random approximate posterior mu y hat n pos. And we have error bounds with respect to the Hellinger metric or the Kullback-Leibler divergence for this random approximate posterior. So there are some open questions here. One big question is, of course, how do we choose the random model of this error? And this is really a difficult question. It will depend, of course, from problem to problem. And the best thing that I can basically, the closest thing I have to an answer right now is that use everything, the guideline would be to basically use everything we know about the true model and the approximate model that we have. Of course, this information won't ever be complete and additional assumptions will be needed. Another open question that would be of interest is to prove so-called certifiable versions of this bound. And what I mean by certifiable are basically a way to actually calculate this quantity. As you might notice, an expectation with respect to the prior, that's quite complicated to compute in practice, because typically your parameter space will be very high dimension, and integrating over high dimensional spaces is really difficult. Another thing which I've kind of swept under the carpet is this estimating this D is actually quite complicated. All right, and with that, I'd like to end with references and thank you for your attention.
Thank you, and can you hear me? Yes.
Yes, I can hear you.
Yes, thanks for the nice presentation.
Thank you.
We have some questions here. Yes.
Hello, Han, Sebastian here. I think there's something wrong with the microphone now.
I can hear you.
Okay, good. So I didn't quite see in what sense the randomness is helping you. I mean, do you get better bounds? I mean,
all right, so that's a good point. So from this bound, it doesn't actually, you can't actually tell that you get anything from the randomness. And for this, I would basically, the best way to answer your question is in terms of coverage, right? So this is the example of the Fitsunagumo problem. And the task here was to basically infer the parameter vector theta 1, theta 2, theta 3. For plotting purposes, I'm only going to show you theta 2 and theta 3. And so the key takeaway and how I'd like to answer your question is that if we don't randomize, basically what we see is that the posteriors that we get from using the approximate forward model without randomization, they are really concentrated, and they're concentrated far away from the truth, right? Of course, as you reduce your time step, so going from blue to yellow, ultimately to red, as you reduce your time step, the error in your forward model in this example will go to 0. And that's why your posteriors, even though they're biased, the bias goes to 0 as well. But of course, in some cases, it's really not practical to let your time step go to 0. This could be, for example, in multi-level Monte Carlo. We want to invest as much effort in coarser solves where we can get better statistical information and really minimize how many solves we want to do at the finest discretization. What we get from randomization, I would argue, is basically wider posterior coverage. It's kind of variance inflation, but what we gain is that even at really coarse steps, so the blue line here, we can still get pretty good posterior coverage of the truth, which is basically where the dashed lines intersect. And that's not always the case when we don't have randomization. Of course, this is just specific to this Fitsunagumo initial value problem. It will depend from problem to problem, but the main idea is that to try and get better posterior coverage, or conversely, to account for this error in the forward model that we work with, the approximate one. I hope I've answered your question.
Yeah, no, thank you. That helped a lot. So maybe you would want to look more at the statistics of these empirical or these randomized measures then, right? I mean, not just look at expectation values in your analysis, but also. Definitely.
Yes, definitely. So one thing would be to see, can we prove, for example, high probability bounds, concentration bounds, but that would be very interesting. It's something which has been discussed before, but at the moment, I have no results on that front to show you. Thanks for the question.
Later, okay, there's two.
Thank you very much.
Thank you very much.
Is it on?
Yeah, I can hear you.
Yes.
Okay. Thanks for a nice talk. So my question is actually related to this same question that you just had on the same picture. So I appreciate that when you add the noise, you get the spread. You get, I guess the true parameters are in your posterior somehow. But I think what's important in practice is that if your forward model is not very sensitive to the parameters, then actually it doesn't really matter if you get the true parameter in the end or not. So in that sense, I don't see much gain really, because that spread is still leading you to a lot of uncertainty.
Yes, you're right. I mean, and this is where I would again say that whether or not you choose to randomize, it depends a lot on, exactly as you said, does this error in the approximate forward model, does it matter a lot? If it matters a lot, or if one has the feeling that it matters a lot, then I would argue it's important to try and account for that error somehow. But I completely agree with you. I mean, there's a trade-off to be made here, right? As in all statistical problems, there's always some kind of bias variance trade-off, and that's pretty much inescapable. One doesn't want to inflate the variance too much because you're going to screw something up somehow, or you're going to lose something somehow. Pardon me. But I would say this depends a lot on the forward model that one has at hand. If one is not very confident in it and suspects that maybe it is a bit sensitive to the parameters, then in that case, it might be beneficial to do some randomization. But I agree with your point.
Okay,
Yeah, just a quick question. So you said in passing that the estimate on the Hellinger distance in terms of G minus Gn doesn't depend on N. But does this not come back in once you look at this maximal inequality? So at some point there was max 1 over N. So there it doesn't depend on N, I see that. But then at some point you have to have a maximal inequality. Right. And I don't see how you get any cancellation there. So does this not become worse and worse with N becoming large?
So I think what you were referring to was perhaps, so here, let me go to this result. Perhaps here, was that what you were talking about?
Well, I think so. So this would then estimate the right-hand side of what you had before, right?
Right. And then your issue is that, are you concerned that there might be some constants here that blow up with N? Because H here would be.
I cannot see how this does not depend on N ultimately.
Well, here I've chosen H to be something like the length of the time interval T divided by capital N. So what I would then like to do is that if I think of N as basically my approximation resolution, and I would like my approximation to be better as N goes to infinity, then this right-hand side as N goes to infinity will go to 0.
Okay, thanks.
Yeah, I'm sorry if I didn't answer your question, but I would be happy to discuss this later if you wish.
okay. Do we have more questions? If not, do we have online questions? Okay. Okay, then let's thank the speaker again. Thanks, Han.